also now there's like this convenient sort of thing you can look at where it's like, here's a code base. If you would like to access the debug information for your own programs, to write your own instrumentation tools, your own inspection tools, your own metaprogramming tools, whatever you want, now Rad has done that for you, or Epic has done that for you, right? And so this project has a lot more cool stuff in it than just the debugger, because they chose to tackle a bunch of other hard problems at the same time and succeeded.
I got a question for you, Ryan. As someone who also worked at Epic, but a different one, how often, like on a weekly basis, after you tell someone you work at Epic, do you get, whoa, bro, that's epic? Every time, like, because I feel like you're like, guys, come on. Everyone said that joke already. You can relax.
Yeah.
You know?
It definitely happened. It's funny because I was wearing an Epic shirt to a hospital at some point.
Oh, they like,
Yes!
and they're like, hey, can you help us with this quick? Like, bro, just like fix my chart problems really fast.
Yeah. And like, it was one particular shirt design where you could see Epic very clearly from a distance, but you couldn't see the games part very clearly. And so they were like, oh, Epic, yeah, we use Epic here. I was like, don't tell me they're putting Unreal Engine, like, in the MRI machines or whatever. Like,
it's a brand new therapy. We put them on Fortnite. It's like the days go so fast. Before you know it, you're healed. You know, it took 6 months. But
all the surgeons are like flossing in the room, like they're like doing stuff. And you're like, what is happening? And they're like, it's an emote. Sorry, don't worry about it.
They always emote after a surgery.
Yeah,
like, crushed it, bro.
Yeah. New heart. Closed up that valve.
All right, so I have a pretty serious question. Since you do work at Epic, do you get free Fortnite?
Isn't Fortnite already free?
Yes. The Sabrina Carpenter skin. Can you get that for free? Is what he's asking.
Oh,
just asking for a friend, okay?
I see. I haven't tried, but I can check for you. I'll let you know.
At my Epic, they had my favorite phrase, which was consider your salary a stipend for that. Like, whenever people are like,
are you kidding me?
Why isn't gym membership included in our paycheck? Right? Because, like, that's the big tech thing to do is, like,
right.
we're going to micromanage your life and give you $100 extra a month to pay for, like, a gym.
Right.
And I loved Judy on stage, like, 12,000 people answered at one time, like, consider your salary a stipend for that. And I love that so much. I was like, yes!
They're like, what do you think we are, some kind of healthcare company here?
Well, they did give really good health insurance. I missed that after I left. They were like, but yes. But it was good.
They probably just hack into, like, it's running all the systems. It's just they set all their employees to $0 every time, right?
Yeah.
It's like, we're providing healthcare.
0. Yeah.
Oh, yeah, the other thing about the Epic misunderstanding, TJ, is not... So... you probably don't have this side of the problem. So they're like, oh, you work at Epic, and it's like no, not that Epic. The one who makes like Unreal, and they're like, oh, that's Unreal. So there's like two words they can say.
Back.
Yeah, exactly.
Dang.
So that gets rough. But
I just had the look of like intense sadness when they found out I didn't make Fortnite. Like the only thing they thought they were going to be able to connect with me on. Like, I'm a software developer. I work at Epic, and they're like, oh, cool, something interesting, and I'm like, no. Electronic medical health records, and I work in an insurance and billing section.
Yes.
They're like, well, that's kind of cool too. It's like almost like making the world's biggest video game. It's almost there. What language do you write in? Oh, mumps. The conversation's over.
I did a little bit of programming in college. What is it? C++? C? Oh, mumps. Oh, okay.
What the hell is mumps?
That's the language that they use at Epic. Oh, that's right, Casey. You weren't there for when we talked about...
The hell is mumps? That's a disease.
It's a disease.
Why is a healthcare company programming in a language that's named after a disease? What the hell is happening?
Casey, but this is like, why do programmers think of dumb names? Because they're stupid.
What is mumps? Tell me. No, I want to know what mumps is, though, now.
It stands for, like, Massachusetts University Multi-Purpose System, or, like, something like... It's like they made it at some hospital in, like, the 70s or something like this. I don't remember exactly.
All right.
And so they don't call it mumps anymore for exactly this. They call it M. But it's
That's
mumps.
not better.
They just call it M.
That's very confusing.
Well, yes,
what is James Bond now? Like, it's like, that's Q and that's M.
They also skipped like D, E, F, G. Like they started at C and now they're at M. It's
yes,
very
but
confusing.
guys, there's trade-offs. The option is presenting the doctors with this was built with mumps or this was built with M. Okay, they're gonna say something. Fine. Sometimes they say InterSystems Cache because that's one of the people that provide it. All right.
I would just like to point out that basically all of the D language stands out there are now furious at Prime for saying they skipped D. Wow, that's gonna hurt some people.
Dude,
at
all
Prime.
Hey,
one of them.
Wow.
Yeah, all 7 of you in the comments, let us know that you've written a line
God.
of D.
Oh my God.
Wow. Oh, we have
Brutal.
garbage collection and manual memory management. Oh, but you don't have users, okay?
Yeah.
So,
Hey, what's one thing that both C++ and Rust users can agree on? D sucks, right? Like it's very, very simple.
Oh my God, you guys. All right, I'm not involved in this. This is nothing. I don't wanna
Casey.
have a fight with D people.
we're cutting that out. We're putting the whole thing in here, and we're putting in a you laughing. We're just going to splice you out of context.
Oh, yes.
I should
Casey,
never have let you guys have edits. You
do
should
you-
never have been able to edit
Do you
these.
actually know anything about D?
Me?
I do, yeah.
Yeah, yeah. You can
A
just
very
say
little
what's
bit.
D. You
A
can
very
say
little
it.
bit.
You can just say that if you need to.
What?
Casey, but explain this then. If you're such a big fan of D, then why is it not D moratory?
Yeah. That's
I'm not a
great
fan of
question.
D. I'm just saying, like, I don't.
Oh, we got him! He's not a fan of D. Cut it.
Oh my
Spice
God.
it up, boys. Put it in.
All right, well, thank
All
you,
right.
D. Moratory, for that. You know, I'm not going to lie to you, Ryan, you've been suspiciously quiet about Oodle. Could you please explain why you haven't talked about Oodle once yet?
What? He doesn't work on Oodle.
Yeah, I don't work on it.
Obviously, you'd use the compression in all of your debugging, so I would assume so, at least.
I don't actually, like, the only thing I use like one header file that Jeff gave me for compressing, but I don't even think it's any of the Oodle stuff.
Okay.
It's just so I'm very Oodle adjacent, if you will.
Do you want to talk about Oodle Prime? We
No,
could
I
ask
don't,
Charles
actually.
or Fabian. Okay, I'm like, they would come on, and probably one of them might. I don't know if you want to talk about Oodle, but
I just wanted to ask an Oodle question at some point, okay? It was very important to me because it's such a funny name.
okay, we'll do an Oodle stream next time. This time, though, could we talk about debugger information stuff? Because I'd like to talk about that.
I actually
Yes.
will. Can I do a real follow-up question?
Please.
You said something, Ryan, inside your talk, which is how do steps work? And I thought the same thing. I'm like, how do magnets work? How do steps work? And so, can you explain why that's such a tremendous problem?
Yeah, so I don't know what a magnet is exactly. Maybe
Yeah, no one.
You
does.
don't have to answer that one. It's
Yeah,
not possible.
This is not going to be. We don't want this to become a Christian stream right now, so please don't answer that question.
They don't know the reference, Prime. They don't know the reference.
No, he does know the reference. That's why he said that.
No, I don't think he knows the reference.
Take a look at this fine creation and enjoy it better with appreciation.
I don't think I know.
Magnets work. He doesn't know. That's fine. Neither
really?
does chat. Move on.
Okay, got it. Okay,
we
I think
killed him.
that.
Well, that was the perfect response if you did know, though. That was like so good because we don't know how magnets work. I mean, no one does, right? That's the whole point.
Yes.
I see.
Thank you, Casey.
I see.
All right.
Okay,
All right,
so
let's
I
get
can
off
explain
theology,
how.
Let's get back to this. How do steps work?
Okay, so line stepping is. Okay, I guess the first thing to understand about the problem of stepping is sort of how a debugger interacts with like another running program in like another native running program on an operating system. So basically the debugger has the opportunity to like make changes to memory and make changes to registers, and then it can suspend or resume certain threads. Like you can basically set up certain threads to run or others to not. And then it just says go, basically. It can just say to the operating system, okay, now you can schedule this program's threads again. And then like the debugger loses all control at that point until that program does something that would cause the kernel to transfer control back to the debugger. And so if you think about what it actually means to like step over a line of source code, first you have the problem of like locating where the where a thread's instruction pointer, because you're stepping a thread over some line of source code that it's on. First you have to like extract the register value that stores the instruction pointer of whatever thread you're stepping. You have to then understand where that actually what source code that actually maps to. Once you know that, you know the range of addresses that are associated with that particular line of source code that thread happens to be stopped on. And then you have to say, like, let me, basically I have to produce the effect that this thread will stop execution, like the program will stop execution when this thread leaves this line of source code. Now, a very naive algorithm you could do to do that would be to say there's something on CPUs where you can single step a thread, which at that level it's just stepping over one single instruction, and then it immediately interrupts. So you can basically set a bit in one register on the CPU, and you can say, okay, step over one instruction and then stop.
Can I interject one thing real quick here for the folks at home? So just to be clear for anyone who hasn't looked at this kind of thing before, so when you have a line of source code, a compiler is turning that into potentially many assembly language instructions that will actually be executed by the CPU. So there's this mapping, and not only is it a like one to potentially many mapping, meaning one line of source code could produce many assembly language instructions, but also in more sophisticated builds, like when you're running an optimizer, those assembly language instructions do not occur in a chunk. So it's not like going from one to like 3 instructions in a row. It could be going from one of your source lines to several instructions peppered throughout other instructions it has been mixed with that come from other lines of source code, right? Yep. So the mapping is very messy, and one of the reasons that debug information is not a super easy problem is because the whole point of that thing that Ryan was talking about before with PDBs and dwarf, like this debug info that gets produced when you build your program, one of the reasons that's so messy is because that is trying to store in some way that a debugger can use, among many other things, how do you go from a line of text that the user typed into Vim, right, to which assembly language instructions the CPU is going to execute, which ones it caused, because when you're going through an optimizer, it's combining instructions, it's like removing instructions, it's reordering instructions, and so even just that one part is messy. So everything's Ryan's talking about now when he's saying how do you go from one to the other, like just keep in your head that it's a very messy mapping between those two. That's all I wanted to throw in there.
I had to also throw in just a quick question to answer along the way, which is when you breakpoint or you hit some sort of stopping condition and you're in the middle of a line, does that ever happen as well? Like where you're just like, I'm halfway through a line, what line do you appear on? Does that screw up debugging information that causes confusion? I'm very curious about that.
Yeah, so that definitely does happen, and it can even happen, like, for example, if you step out of a function call, like you're inside of a function, you want to return to whoever called you. Generally, like, there might still be some instructions to execute after you've actually popped from the call. So if you do a step out operation, you'll end up in the middle of the line. You're not just at the first address of the line's source machine code. You might be at some instruction in the middle. And so basically, that's just an extra wrinkle in the problem. You don't, it doesn't really screw anything up, but you just basically have to say, like, this is a range of instructions, and if the thread ends up anywhere in here, I have to associate that with this particular line of source code. So it's one detail in the mapping, but it's not like a showstopper by any means. So yeah, if you wanted to step over a line of source code, if you wanted to like basically proceed this thread until it has exited this particular line of source code, you one simple thing would be to single step that thread until you see it has left the line. Like you just keep mapping the instruction pointer every time it comes back, and then if it leaves if it's changed the source code line that it's on, then the step is done. So that's a very simple algorithm. It also is enormously slow because remember that each one of these interrupt instructions that comes back, each one of the single step after a single step has completed, basically what's going to happen is the kernel is going to schedule that thread and it's going to say, okay, execute one instruction. It's going to immediately trigger an interrupt. The kernel will then it'll switch to the kernel, and the kernel will say, okay, now I need to report this debug event to the debugger, so it has to transition, it has to context switch over to the actual debugger itself. And so every single time you do a single step, it's one of these round trips. You can think of it as between the debuggee or the target process and the debugger itself. And so if you've got a line that has 100 or 1,000 instruction, I mean, you can make it arbitrarily long, really. You're causing a round trip every single time someone every single instruction within that line. So that gets very slow. So instead what you kind of want to do is say, like, I'm going to set up a bunch of, there's another concept that I should introduce, which is the int3 instruction on x64, but there's equivalents elsewhere, where you can basically put a it's a 1 byte instruction that you can use to overwrite any instruction, basically, because it's just 1 byte. So it's the minimum instruction size. And you can go ahead and say, I'm going to put this here, and then when the thread executes this instruction, it's called an int3. And when it, there's other kinds of interrupt codes, but int3 specifically is this 1 byte instruction that you can put anywhere in the code stream. And when a thread executes that, it'll immediately interrupt. So it has the same effect, sort of, as the single step, except it's caused by an instruction you put in the code. And so then so in order to avoid all of these round trips, what you can start doing is saying, when the thread is in this line, and I say step over this line of code, I'm going to basically set up an int3. It's called an int3. It's also called a trap, is what people call it. So what you can basically do is start putting these traps anywhere you think the thread might go within this line. Now, if it's pure linear code, like it's going to do a bunch of mobs and then an add and then, whatever, very simple linear code, there's only one trap you actually have to place, which is at the beginning of the next line. But it starts to get more complicated if you, for example, if inside of that line of source code you've got a jump instruction or a call, then you have to start thinking about, like, where are all the places this thread might actually go to? And so then you might have to start doing things like, okay, let's disassemble the line, let's figure out, like, where the control flow will lead to in this line, and let's go place traps in all of those places. And then it gets a little bit more complicated too, because, for example, if you're in a recursive function call, like, so two variants of stepping exist for people who haven't used debuggers. There's step over and step into. There's a lot of other steps you might imagine doing, but those are the two, like, common ones, and step out. Step over will basically, it won't follow call instructions. So if you do a step into, you're sort of stopped at a function call and you want to go into the function call and see what's actually happening inside of the function call. With a step over, you don't care about what's going on inside the function, so you just want to step to the next line and have whatever happens inside the function happen. Now, if you wanted to do a step over, you could imagine if you are in a function that is recursive. And remember, a debugger has to deal with any code that someone could write and feed into it. Like, it has to kind of handle all these cases gracefully. There's lots of recursive code that exists. So if you're stopped at one particular line and it's a recursive call into the same function, it gets more tricky, because if you just place a trap at the next line and then you try to step over, you're going to hit that same trap address, but in one layer deeper in the call stack. So you basically have descended to the next call, hit the same trap, but it wasn't actually a step over, because the step over, it didn't step over the line, it didn't step over all of the call work that happened. Now you're one layer deeper in the call stack, so there's no way anymore to actually step over that line of code. So you have to get tricky about, like, okay, has my stack pointer changed? When do I update which value of the stack pointer that I want to check against? It becomes kind of basically like a little program you have to send down and say, like, if it hits this trap, do this, and if it hits this trap, do this, and if it hits this trap, then single step here, and, like, it becomes a very complicated sort of state machine that you actually have to implement.
So hold on. Can I get one more? Oh no, TJ wants it.
I just got just a quick question. I was just wondering, like, on average, what your step count is every day. You know what I'm saying? Like, because for me personally, like, I don't know if this makes me a debugger, like a step debugger or not, but, like, I've got my own, like, walking treadmill now at my desk.
Yeah.
So I didn't know if this is kind of like what scenario this kind of goes on. So I just didn't know how this related to debugger. Does this make me a step-driven debugger? Like, if I'm reading...
you're stepping into, you're not stepping over.
Over,
and so
yeah.
we're talking about stepping
Right.
over right now, TJ.
Yeah.
Okay, I'm trying now.
There you go.
See,
Yeah,
like, I'm
that's
trying
more,
to step
that's
over
the
now.
harder one to do.
Which one is harder? How
You
do I
are
do
putting the-
recursive treadmills?
You're on an int3 and it's
You
inside
put
the
that
stack.
treadmill on
Yeah.
a treadmill.
Oh, that makes so much more sense. And then
Yes.
it's running too.
Yes,
Yeah.
exactly.
Right.
I got it. Okay.
Okay,
All right.
Prime?
Anyways, you can continue now.
Yeah,
Thanks.
okay. TJ, how long? Okay, now we have a sub question. Now our stack has been pushed. TJ, how long have you been waiting for that? And also, you have just a black square in your screen.
So
I saw you raise it like 10
immediately-
minutes ago.
Immediately after we started talking about step stuff, I put it into standing mode, and I was getting ready. I had to set up that scene. I did not have the video thing ready before
Wow.
this, so I probably heard about 5% of what Ryan said, but I was so excited for this joke.
Wow. Okay.
I was
Commitment.
so
That's
excited for
commitment.
this one.
That
all right.
that is some serious professional level podcasting. All right. All right.
So when it comes to stepping and putting in all these in threes, do you also have like because I don't precisely understand how jump instructions work. I believe there are relative and absolute ones. Does that mean you also have to update all the relative instructions around all these places that you put these in threes? Because theoretically, you shifted down some amount of the assembly.
So
You're not
actually
inserting.
Okay,
Yeah.
I thought you were dynamically at like runtime being like, okay, like they're stepping next. Let's actually insert some stuff into the program.
You're overwriting it. You're
Yeah.
over. That's why it's crucial that in3 has a 1-byte version, because you're romping it over the instruction. One of the things Ryan didn't mention, because he had to mention like 8,000 things because this is incredibly complicated, is that actually when you put that int3 in there, you have to remember which byte you overwrote, because once you are done stepping, you have to go replace all of those with the bytes you overwrote. So that happened as part of this process.
Oh my gosh. Okay,
Yeah.
so does that mean when you literally overwrite assembly, and then
Yes.
when it hits that int, you then have to put back in the correct
Yes.
assembly so that when it executes the line, it correctly executes the line?
Correct.
That's crazy, dog. That's great.
I don't know. It sounds like probably debuggers. It's as easy as making a regular CRUD app, guys.
Dude,
I
have
mean,
you seen a banking app though, Ryan? Do you have any idea about a banking app?
Yeah.
Yeah, I can't even imagine. It's just.
That's like magnet level stuff right there. The banking app.
Yeah.
How
do
do
they
banks
even
work? Actually, we don't know.
Actually, if you would have been paying attention to Twitter, Lori Wire just tweeted how AHC works, which is literally FTP. So
Yes.
All right.
we
there
do
you go.
now
Cutting
know how
edge.
banks work.
Yes, we do.
Right.
That's why it. Anyways.
So
I'm not gonna get distracted.
underlying all of this, right, is like this is also why you may have noticed there was a little snippet of Ryan at the Better Software Conference doing a little thing with Wukash, where he asked him like, what was the one OS feature that you would like to have that you don't have right now? And Ryan said, I would like to have user level int3. And it's like, what is that, right? And that underlies this entire thing. So what happens is, in the CPU, right, there's this thing called the interrupt table, or there are things called interrupt tables in CPUs, right? And the reason for this is right at the beginning. This is in like 8086. Like the original 8086 chip has this. This is not like a new thing. They've been upgraded over time to have different capabilities, but generally speaking, this exists for a very long time. So they have these tables because what you often want to do is you wanted to have some kind of like higher level's the wrong term, supervisory system level, should I say lower level code, operating system code, whatever. You want to have some code that you can trigger from anywhere instantaneously, meaning you don't have to like know in advance that you were going to use this code at this time, right? A call is when you know you were going to use it. At this point in the code, I call this function, right? This is like, we have no idea what we're going to do. We just suddenly have to do it. And one of the big reasons for this originally is like servicing hardware. So the CPU has to read something from some bus on some hardware, you know, like the original keyboard input or whoever knows what's happening, right? And so what would happen is an interrupt, literally the reason it's called an interrupt, int3, interrupt 3, an interrupt would happen that stops the normal execution, what the CPU was doing. It looks in a table for what it should start doing. It goes and does that, and then it resumes back to wherever it was in the program. It's literally what it sounds like. It's an interrupt. And this was used for doing things, like I said, like reading hardware and stuff like that, because bytes would like come into the CPU that it had to like look at right now. So it would stop the program, you know, this is back when you didn't have multiple cores or anything like that, right? Stop the program as it's executing right in the middle of whatever it's doing, go service this interrupt. It's called servicing the interrupt, right? Go jump to that code, do it, right? So what an interrupt really is it's basically, it's the same kind of thing as a function call, but it's one where you didn't know what was going to happen. It's a function call that happens out of nowhere. And the reason that this is very useful for something like debugging is because one of the things that a function call will do, right, is it's going to save what the instruction pointer was before it does the call. So it will put the instruction pointer onto the stack, right? This is a call instruction. We'll put the instruction pointer onto your program stack. It then transfers control over to whatever the location is you're going. So it changes the IP to point to whatever the function is that you wanted to call, does that, and then when it goes to do a return, it will pop off the stack whatever that instruction pointer was. So it's basically a thing that uses your program stack, your standard program stack, to track where you are in the program. That's a normal function call. An int can't do that because it doesn't even know if there is a stack. It's happening in the middle of any code. There may not even be a stack frame. You may not even be using the stack pointer as a stack frame at that time, technically, in 8086. So what it has to do is do some special work to preserve, right, like the IP in this way that will, like, we know we can preserve just what the instruction pointer is. Then we're going to go into whatever, we're going to look in this special table that the CPU literally has a hard-coded register that tells it where it is. So it's separately stored, right? We're going to go there, look up where we should go. And by the way, nowadays, we also look up a bunch of information like whether we should be transferring control to like a different level. Like, should we be dropping down to ring 0 from ring 3 and all this other stuff, right? So there's a whole bunch of crap in that table. And off you go. So the way debuggers are written currently, because they have to be, is on something like Windows, they are written as a user-level application. Which is fine because that's roughly what you want. You don't want your debugger to crash to take down your whole system, right? You don't want CrowdStrike happening here, right? So you want the debugger to be running at ring 3 on Windows so that it's running up like a normal program, and if it screws up, like if Ryan on like the one bug he has, right? If you hit that bug and it crashes your system, you just want the debugger to crash. You don't want your whole system to blue screen. So it's good that it's doing this. But the problem there is it needs to do all the things that Ryan just says. It needs access to the memory. It needs to be able to put in like these things like int3s that will happen. And the problem is when you are at user level, right, the kernel doesn't want you doing stuff like messing with the interrupt table or, you know, saying that you're going to be the person who gets whenever an int3 happens on this core, that you're the one who's going to get it or whatever, right? It didn't want any of those things for security and stability reasons. So as a result, the debuggers have to do all of the work that Ryan described through an API that the kernel will then use. You know, it takes your API calls and goes, oh, I see. You wanted me to tell you when this guy hits an int3. So you go, you know, I'll let you access his memory through my memory mapping APIs. You go, you poke it in there, you poke your int3s wherever you want, great. When the int3 gets hit, the kernel's the one who's going to get called, not the debugger, and then it's going to go through the API to let the debugger know that it happened. What this means is that now all of these things Ryan's talking about, every one of these traps that gets hit, is a full round trip. Debuggy is running at ring 3. The trap gets hit, the int3 gets hit. It's got to drop to ring 0, wakes up the kernel. The kernel goes, wait, what is happening? Oh, right, this is a debugged executable. I know I should tell the debugger about it. Okay, let me re-switch the task over to the debugger's context. Let me wake up the debugger in ring 3 and resume execution of a debugger thread to handle this. The debugger then goes, what just happened? Oh, the kernel told me I had a trap. All right, let me go fix up the trap things. Let me set any new traps that I need, and then let me retell the kernel back at ring 0 to resume the debuggy. Back we go to ring 0, it then switches in the context of the debuggy, back up to ring 3, and we resume where we were going, right? This is wicked frickin' slow for so many reasons, right? And so what Ryan was talking about is, hey man, what if we could just set the int3 to just jump to something in the actual, the person who's being debugged, that program? The debugger could like JIT compile some code that just does the trap operation that it wants to do and resets whatever it needs or anything else, right? Checks conditions, anything it wants to. We just set the int3 to not do any of that. Don't tell the kernel, don't take your in transition, just jump right to that thing, do the stuff, and then resume. It would be so much faster. Getting rid of that, like, first ring transition, back up ring transition, back down ring transition, back up ring transition, right? It gets rid of all of that. So that's what he was asking for, and this would be like a huge feature. If there are any kernel devs out there watching, please add this. User-level interrupt handling like this would be so useful. And then that thing, if it actually wanted to do that huge transition thing, can just have a syscall that it does called actually transfer control to the debugger, right? So anyway, whole big thing of coolness there. We can't do
All I got from that is horse and debuggy is slow. That's what I got, Casey. So
I tried so hard, Ryan. I tried so hard.
TJ
actually makes
also
sense. I
tries
just
hard.
wanted
That's
to do
the
that
problem.
pun. Sorry.
Anyway.
Yeah, like one example of, so at a high level, what you might imagine doing in a debugger that uses that sort of where you want that kernel level feature would be if you set a breakpoint on a particular line of source code. If you like run your program within the debugger, you say stop here. That's like reasonably fast, because those two transition or three or four transitions actually. You pay that cost once, and at the scale of like, oh, run to this line, it's not really noticeable.
And you wanted to come back to the debugger anyway, so it's like doing what you wanted, roughly, right?
Yeah. So when that gets when you actually really have to pay that cost to a sort of prohibitive degree in many cases, is when you wanted to say, stop at this line of source code, but only if this condition is true. So conditional breakpoints are like super common debugger feature. And it's like kind of the first version of fancier stuff that a debugger would want to do. But this is where it gets really slow, because then basically the debugger can't like do this installation of code that checks the condition inside of the debug. And so what has to happen is it hits the int3, controls transferred back to the debugger checks the condition, it evaluates some expression, it like does whatever evaluation stuff it needs to do to check the condition, and if that condition is false, then it goes back to the debug. And so if you imagine you put this in a loop that's supposed to run a million times, maybe it happens instantly normally, but because you're paying this round trip cost every single time the thread hits that int3, it just becomes like prohibitively slow. Now if you're doing it once per frame, like it's still worth it for debuggers to have conditional breakpoints today, but they're like dramatically pessimized just from this problem. But if that problem were addressed, you could start doing lots of other things. Like another thing, something like printf debugging is profiling, like inserting profiling markup into your program. Like if you wanted to say, oh, I want to sample the time here, let me measure that, build me a flame graph of this kind of thing. That is the same problem as print debugging, where it's like, okay, go back to the source code, insert the things that I was looking for, build the program, run the program, get back into the state that I wanted to be looking at, and then inspect the log. And then it's like, oh, I need to drill one layer deeper into this like flame graph here, but I didn't add the markup there. So let me go back to the program, add the markup there, and you can't do it too much. You can't do it at every function, for example, because then, that profiling cost will start adding up like dramatically, and then you won't even be able to see what the actual performance costs were. So what the debugger could do is like, let's just do that dynamically. In the debugger, let's say, add a line of markup here, like a sampling line here, add a sampling line here, and then it could gather that data completely dynamically. It'd be way faster to like drill down into problems when it's really uncertain what you need to be looking at, basically. So yeah, that's like the high level, what you would expect as the user if you had this kernel level feature, basically.
Yeah. And so what we have to do now, basically, right, if you want to do this kind of thing, you can still do it, but what you have to do now is you have to handle a crap ton more edge cases, basically. So what happens is, if you want to, you can still do effectively this by not using int3, right? Because remember, the important part about int3 is it's a 1-byte instruction. So even if it's overwriting another 1-byte instruction, it's okay. All the code will still work exactly as it should, because you only have the int3 just exactly where it needs to be, and anyone who's like jumping to the byte immediately after that, doing something weird or who knows what, it's fine, right? However, if we wanted to implement a feature like this without the assistance of int3, or halt or any of the other instructions that go through a table and are 1 byte, right? There aren't very many. I think there might only be those two. I don't know if there's a third one, but anyway. On x86 anyway. So if you want to do that without this, and Ryan has looked at this sort of stuff, and this is the kind of thing people are currently doing, so this is how you have to do it, you have to input some kind of a jump or a call actual instruction there, which takes more than 1 byte. So you can still do everything we just said, but you have to overwrite the thing you were going to overwrite with several bytes, potentially. And when you do that, now you run the risk of, if those several bytes overflow and go into the next instruction, that could have been instruction that someone was jumping to. So now we have to do all this checking to figure out, like, is someone jumping into the place that we had to overwrite to, and blah, blah, blah. So now what should have been a very straightforward extension of just patching in an int3 and everything works perfectly and guaranteed no problems, what should have been a perfect extension of that is now this huge, like, did we catch all the corner cases? Oh, crap, it doesn't work in this one place. And now we got these bug reports from these guys who were doing this thing. And, and so if the kernel could just add this feature, all of that complexity goes away. And there's, like I said, so this is a thing that people have done. It's not like you can't do it. It's just it turns what would have been a very simple problem into a very complicated problem. And so that's why it would be great if the kernel could do it.
Kernels are great at that.
Yes. That's why we
Turning
call them
simple
kernels, because they're like a kernel in a military thing where they... I don't actually know.
I
that's
like
a
it.
good
Casey,
one.
keep going.
Yeah.
We'll
going.
cut it out in post.
Where does
Try
the
again.
colonel keep
Shoot
his
it.
armies?
Shoot for it again, Casey. Here, it's like the kernels are great at that.
Yeah, just like, we're going to take it Mayday. Beep! Yeah.
So are all these things you're describing effectively gone in things like JavaScript or in any interpreted language which has a VM? Because then the VM can go, well, I can just insert an interrupt like right into the bytecode. I don't even have to worry about it since I'm processing these things. Do a lot of these problems effectively, because the Chrome debugger is actually shockingly a great debugger.
Well, okay.
Well, I mean, you got to remember you're debugging JavaScript. There's not like a lot, it's
I've had a
simple. It
lot
does
of...
have all-
I've been not that happy with its accuracy in catching breakpoints and things like that, actually, so I would not categorize it as a great debugger, personally.
Really?
I would
never had
say
any
it's a
problems
pretty
with
mediocre
breakpoints.
debugger, in my opinion.
You don't even program JavaScript. Don't even try
I do.
this with me,
I
Casey.
programmed a lot of
Casey, I already
JavaScript.
know
Yeah.
that this is a trap. This is an int 3. I am not getting bamboozled here, Casey.
I have used that debugger a bunch. I had to use that debugger on Electron even prime. So I used it
Okay.
locally.
That might be different though.
Local
That might
Electron
be-
fun, and that was a
Yeah.
huge ball. Like that was great.
Yeah,
that was
that might be
fantastic.
different. I'm not.
It's not.
Gonna-
It's the same.
yeah.
But I've used both of them. Yeah. I feel like it is not reliable. It's not reliable at a couple things. Restarting and catching breakpoints when a web page is reloaded, I have found it to be
okay,
fairly unreliable,
Yes.
actually. And that's a very important thing, because if you're trying to debug stuff that happens at startup, right, like at load time, it just... And so, it's one of those things where I didn't... When you use a debugger, you get this feeling of, is it solid or is it not solid, right? Not
I think I know
the
exactly your problem.
SOLLD
Okay.
like acronym SOLID thing, not Liskov substitution principle, but like, is this thing reliable so that if I set a breakpoint, I know for sure that this code only got executed when the breakpoint got hit and no other time. And I definitely can guarantee you that was not
I think
true
I
of
can
the
actually
code.
explain that one. That
Okay.
one I think I can explain, because if you use the keyword debugger inside JavaScript, you'll actually get it every single time. But if you use the actual Chrome debugger to do that, it uses the CDP, the Chrome debugger protocol.
Okay.
And so it has to do some sort of async communication with your process, which if it loads fast enough, you're going to miss that entire plane. Is what I'm like 99% sure that's what's happening, because I've ran into a bunch of these issues.
Okay.
Working on that protocol.
Oh, so
on
now
various
you
things.
run into the issues, Prime. At first,
Yeah.
Casey said, yeah. Oh, okay.
It is a great one if you use it correctly, right? I mean, come on.
But that you shouldn't have to, right? The point of a debugger is to save you time. If I have to go research why this thing can't set a breakpoint, it's like, oh, the thing that's supposed to set the breakpoint, you don't set breakpoints that way. You have to use this other thing that's not how you
Idiot.
set a breakpoint to set a breakpoint. Like, then that's worthless, because again, I could have just done printf, which by the way is what I do. I do console.log when that kind of thing happens. So this is why I say I totally understand people who like go, I don't use debugger. It's like, yeah, because when the debugger is unreliable, it's not useful.
Yeah, for
Okay.
me, I just try to not write bugs in JavaScript, and that seems like all right.
Yeah, I don't have any bugs, so that's why I don't use debugger. I don't ever have any bugs, so I'm not really sure. Like, it's cool if you
a
have
skill
bugs.
issue.
I mean, you could use one, I guess. I mean, I
I
don't
get
know.
it. Yeah. I
Yeah.
get why Prime might need one. you
Yeah.
know.
Yeah, that's because I always
Right.
forget no mistakes. It's just like if I could just add that to the end of my AI prompt, everything would be great.
Yeah.
See, that's the problem. You got to put it in the agent instructions, so no mistakes is in every one. See, make it secure, make it good. Don't put it in a Firebase bucket with no authentication.
But also, if we could expound on why I don't think the Chrome debugger is very good. So going further along those lines. So again, in order for a debugger to actually be valuable, it has to do a lot more things than just stopping where I tell it to stop, which already it didn't do. So the other things it needs to be able to do is gather and like marshal and display information to me like cleanly and quickly, right? And
Okay.
it also doesn't do that very well. Like, yeah, it kind of has a watch window that's not absolutely horrible or anything, but it can't do any of the kind of stuff like I love like all the rad debugger features where you can kind of go like, hey, here's my data structures. I want to turn that into tabular data. So like walk this linked list for me and show it to me like it was a table and like all that stuff. Like can't do any of that stuff as far as I know. And if you wanted to do that stuff, you'd basically be like programming JavaScript you'd have to be like writing your own like JavaScript stuff to do that right in there, which again is taking me more time. I just do a console log. And so I think like Chrome Debugger is pretty mediocre. I'm glad they built it, but it's not in the top tier. Like it's not an S tier debugger by any sort.
Oh, we gotta come back with a debugger tier list. Casey, we're gonna do that offline, and we'll publish a video.
I think
so Ryan, actually, could we end with some of that? Can you talk a little bit about like the cool rad debug features? Because like some of that stuff is really cool. Most people don't know you can view like 3D models in rad debugger, right?
Yeah. So the 3D model, like some of it's early. So the 3D model, it's solid, but it's I need to work on each visualizer is like a complicated problem that I have to dig into later. And so, but I do have a 3D visualizer. So basically, the way it works is basically the debugger's got a watch window, and in the watch window you can enter expressions, and they show you can expand them and all that kind of thing. You can also extend these expressions with like visualizer rules. So if you wanted to view the very common example is viewing like pixel data or bitmap data. If you wanted to say, for example, like I have this pointer to some giant blob of data that's just a sprite sheet or some font atlas or something like that. What you can basically say is like, okay, I want to say that this is a bitmap, and then I want to specify some extra information about like what kind of bitmap it is, like how big, how wide is it, how tall is it, what pixel format is it in. And the expression language, like in the debugger watch window, just allows you to express that kind of thing. So you can say like bitmap, and then the first argument it's like a call to bitmap, and you can say here's my pointer, here's my width, here's my height. Those are just expressions, so they can come from variables in your program. And then you can say here's my format, and then you can expand it, and it's going to show you an actual preview of the image itself. You can also like pull it out to your own tab and like see like, oh, like here's a fully featured. At the limit, like once I'm done with it, it'll be fully featured. But it's like you pull it out to a tab, and then it's like, oh, here's a bitmap view. I can pan around, I can zoom in, check the pixel values, and all that kind of thing. Now, every visualization feature in the debugger is sort of implemented in this way. So another common one that debuggers will often support is like a memory viewer, like a hex view of some memory. Mm-hmm. It's exactly the same feature in the rad debugger, where you can say, okay, memory, let me call memory, here's my pointer, here's my size. You can say like number of columns, all kinds of parameters that you want to do for building this hex viewer, basically. You expand it, it's just a memory view of whatever parameters you specified to it. As Casey said, there's also a geometry one. So if you have to specify some pieces of information where you can say like, here's an index buffer, here's a vertex buffer, here's how many indices I have, here's how many vertices I have. I don't know if you need to specify the number of vertices. I have to go look at it. But you can basically say this kind of information, and if you expand it, you just get the 3D representation of like, here's all the geometry data that you actually wanted. And because this is in a watch window, and it's not just like parsing a format that you dump out of your program, you see it update live as you step. So you actually like step over as these vertices are being built, and you can see the vertices change in real time. So it's way more useful than like dumping it and then dumping it to an OBJ and then looking at like some OBJ viewer, like this 3D model or whatever. Same thing with texture data. And so there's also a bunch of other visualization features, like more basic ones, like viewing multi-line text, for example. It's something that every debugger has to do anyways to show you source code, but it's like, you should just be able to apply that same exact path to like just viewing any arbitrary textual data. The disassembly viewer is also implemented this way. It's just a visualizer. And then there's a bunch of different rules that you can introduce to like change how the watch tree, so when you put in like a watch expression, if you expand it, you get rows. Generally they're formed by looking at the members of whatever type you expand or something like that. There's a bunch of ways you can customize exactly how that looks like as well. And that's sort of more like sort of what Visual Studio did with NatViz. It's a very similar kind of, although it's not you don't specify that in XML in the rad debugger, but you can do like the same kind of thing there. And then I guess the final layer, I could dig into more of any of that, but the final layer on top is you can also automatically associate certain types with certain visualizer expressions. So you can go ahead and say, I've got a struct, it's called bitmap, it's got a pointer, a width, and a height, and a format. And I'm going to say, if you evaluate this type anywhere in the program, or anywhere, like if you're in the debugger and you're evaluating anything of this type, just automatically say it's a bitmap visualizer. So you're sort of extending type information. You can put this directly in your program. You can put it in the debugger configuration, like really wherever you want. And then anytime you evaluate that in the debugger, by default, it'll show you that visualization automatically. So that includes hover evaluation. So if you hover the bitmap variable in your program, you'll see the bitmap just pop up. If you put it in the watch window, it'll just be the bitmap. Like it's, you know, that's sort of the final layer to it, where you can basically extend your program's type info to be automatically associated with this visualization information. Now you can always go back. Like if you're like, I don't want to look at it as a bitmap, I want to look at it as a struct because that's what it is. You can always reverse it. There's a way you can do that inside of the visualization, like or within the expression syntax as well. So but yeah, there's lots and lots of stuff you can do, and that's a good first run through, I think.